Welcome back to G Fun Facts Online. On May 30th, 2024, NASA's Curiosity rover was lumbering over a seemingly unremarkable rock strewn across a winding, boulder-choked scar on Mars, known as the Gediz Vallis Channel. The almost 2,000-pound nuclear-powered robot inadvertently crushed the stone beneath its 6 aluminum wheels. When the mission operators directed the rover's cameras to inspect the damage, what they saw completely upended our understanding of the chemical and climatic history of the red planet. Spilling out of the freshly cracked rock were brilliant, yellowish-green crystals of pure, elemental sulfur. Until that exact moment, pure sulfur had never been detected on Mars. While the planet is famously rich in sulfur-based salts called sulfates, finding a deposit of unoxidized, native sulfur sitting plainly on the surface was an absolute astrobiological and geological shock. As Ashwin Vasavada, Curiosity's project scientist at NASA's Jet Propulsion Laboratory, perfectly captured the awe of the scientific community. Finding a field of stones made of pure sulfur is like finding an oasis in the desert. It should be there, so now we have to explain it. Today, we are going to dive deep into exactly why this accidental discovery within the Gediz Vallis Channel has rapidly become one of the most significant chapters in the story of Mars. We will decode the sediments, the boulders, and the unexpected brimstone of Gediz Vallis, and explore how scientists are fundamentally rewriting the timeline of how Mars transitioned from a habitable, water-rich world to the barren desert we see today. To truly understand the profound significance of this channel and the sulfur hiding inside it, we must first understand the spectacular stage upon which it is set. Let us wind the clock back approximately 3.7 billion years. A massive meteor strike punched a gaping hole in the Martian crust, creating what we now call Gale Crater. In the ensuing epochs, Gale Crater was an incredibly dynamic environment. Liquid water flowed into the basin from rivers fed by rain or perhaps melting snow, pooling at the bottom to form a massive, long-lived lake. Over millions upon millions of years, sediments carried by these rivers settled at the bottom of this lake, layer upon layer upon layer. But planetary climates are fragile things. When the Martian climate eventually shifted, the Great Lakes evaporated. This shift was likely driven by the catastrophic loss of the planet's global magnetic field. Without a magnetic shield to deflect incoming solar radiation, the solar winds began stripping away the Martian atmosphere. As atmospheric pressure plummeted and temperatures dropped, liquid surface water became unstable. The once submerged lakebed sediments were suddenly exposed to fierce, relentless Martian winds, which over billions of years carved away the softer surrounding material. What was left behind standing in the center of the crater was Aeolus Mons, known more colloquially as Mount Sharp. It is a massive mountain of sedimentary rock, rising an astonishing 5 kilometers above the crater floor. Because this mountain is constructed from stacked layers of ancient lake sediment, ascending Mount Sharp is exactly like reading a geological history book from the bottom to the top. The lowest layers, where the Curiosity rover began its epic journey back in 2012, are incredibly rich in smectite clay minerals. On Earth, these specific types of clays form exclusively in the presence of stable, neutral pH liquid water. The discovery of these clays early in the mission confirmed beyond a shadow of a doubt that ancient Mars possessed the necessary conditions to support microbial life. However, as Curiosity has painstakingly driven higher and higher into younger geological terrain, the composition of the rocks has drastically changed. The rover recently crossed a major, critical transitional boundary, leaving the clay-bearing units behind and entering a vast region entirely dominated by sulfates. Sulfates, such as calcium and magnesium sulfates, are basically salts. They precipitate out of solution when salty water undergoes intense evaporation. In the grand narrative of Mars, the presence of these expansive sulfate-bearing units was meant to signify the end of the line for Martian water. It was supposed to be a definitive geological marker recording the long, dry death of the planet. But, as any field geologist will tell you, nature is rarely so simple. Cutting directly through this supposedly dry, barren sulfate layer is the Gediz Vallis Channel. From the vantage point of orbital satellites like the Mars Reconnaissance Orbiter, Gediz Vallis is a winding, steep-walled canyon that incises deeply into the northern margins of Mount Sharp. It looks unmistakably like a dried-up riverbed. However, its placement creates a profound chronological paradox. If the sulfate-bearing layers represent a time when Mars had already permanently lost its surface water, how on earth could a massive, water-carved channel cut through them? The rules of stratigraphy dictate that a channel cutting into rock layers must have formed significantly later than the rock layers themselves. This means that long after Mars was believed to have entered a permanent, arid deep freeze, liquid water must have returned to the slopes of Mount Sharp in a truly spectacular fashion. If liquid water formed this channel, it means that fairly late in the story of Mount Sharp, after a long, intense dry period, water came back, and it came back in a big way. As Curiosity approached the channel in 2022 and began traversing its rugged interior, the sheer violence of its formation quickly became apparent to the scientists watching from Earth. The rover spent months imaging and conducting in situ investigations of geological features like the upper Gediz Vallis ridge. Utilizing advanced stereoscopic imaging from the MASTCAM instrument and the long-distance remote micro-imager on the ChemCam instrument, scientists observed that the valley floor is entirely choked with debris. But this is not the fine river sand or smooth pebbles you would expect from a gently flowing stream. The terrain is formed of loosely consolidated, exceptionally poorly sorted blocks of rock. They range in size from a few centimeters to massive, jagged boulders measuring up to 7 meters in diameter. Through incredibly detailed analysis using three-dimensional modeling software, geologists measured these rocks at a specific study site called Region B. They found that their size and chaotic distribution argue strongly against any kind of gentle, continuous river flow. Furthermore, researchers calculated that wind could not possibly have created Gediz Vallis. The channel walls are simply far too steep for wind-driven erosion to have carved them out. Instead, all the evidence points to a late-stage environment characterized by catastrophic, gravity-driven debris flows and dry avalanches. Imagine a thick, violent slurry of rocks, soil, and liquid water. This cohesive muddy matrix would have been capable of transporting massive, house-sized boulders roaring down the mountainside. The presence of these chaotic deposits completely rewrites our understanding of the Martian climate. It indicates that the transition from a wet Mars to a dry Mars was not a smooth, linear decline. The climate wildly oscillated. Water came and went in aggressive, episodic phases. Localized hydrological events, perhaps melting snow or sudden hydrothermal venting, unleashed torrents of debris down the flanks of Mount Sharp long after the Great Lakes of Gale Crater had permanently vanished. Curiosity's exploration of Gediz Vallis was already yielding a massive treasure trove of paleoclimatic data. It was already a wildly successful chapter of the mission, but nothing could have prepared the team for the events of late May 2024. As the rover navigated a field of pale, jagged stones rimmed with bright white halos, it rolled its immense weight over one of the rocks. When the rock fractured under the aluminum treads, it exposed a blindingly bright interior of yellow crystals. Stuck hundreds of millions of miles away on Earth, looking at the raw images beaming back through the deep space network, the science team was astounded. To confirm the chemical makeup of this bizarre anomaly, Curiosity deployed the Alpha Particle X-ray Spectrometer, or APXS, located on the end of its robotic arm. The APXS is a marvel of engineering. It works by bombarding a target rock with alpha particles and X-rays emitted from a radioactive source. It then meticulously measures the energy of the X-rays that are emitted back by the sample. By analyzing these specific energy signatures, scientists can determine the exact elemental composition of the rock. The results from this crushed stone were absolutely unequivocal. The scatter and fluorescence data showed a massive, off-the-charts spike in sulfur. But crucially, it showed a significant depletion in lighter elements like oxygen. Furthermore, the analysis detected absolutely none of the cations, such as calcium or magnesium, that are the standard chemical signatures of the sulfate minerals so ubiquitous everywhere else in Gale Crater. This was not a sulfate, this was unoxidized, native sulfur. Pure, elemental sulfur. Pure brimstone. An extensive report, compiled by researchers associated with NASA's Johnson Space Center, noted that this is the first definitive native sulfur ever detected in any Martian sample. To make matters even more surreal, panoramic imagery taken by the rover's cameras revealed that this crushed rock wasn't just an isolated meteorite fragment that happened to fall from the sky. The entire localized 2,100 square meter field within the Gediz Vallis Canyon was literally littered with similar pale, crumbly stones. Underneath a microscopically thin coating of red Martian dust, the ground was essentially paved with pure elemental sulfur. This discovery sent absolute shockwaves through the planetary science community, and for a very good reason. The thermodynamic and environmental conditions required to form native sulfur are exceptionally narrow. On Earth, pure sulfur is typically found in highly specific extreme environments. You find it near deep ocean hydrothermal vents, within the steaming calderas of active volcanoes, or it is produced as a metabolic byproduct by specialized sulfur-reducing bacteria. One chemistry professor likened the discovery to finding chemicals from a vintage children's chemistry set just sitting out there on the barren Martian surface. It is completely out of place. While it is true that elemental sulfur can sometimes be delivered via meteorites, the sheer volume and highly localized distribution of this massive deposit within the Gediz Vallis Canyon makes an exogenic or meteoritic origin highly unlikely. So, if it didn't come from space, how on Earth, or rather how on Mars, did an entire field of pure sulfur form in an environment that is overwhelmingly dominated by highly oxidized sulfates? Researchers quickly began running complex geochemical models to solve this mystery. According to the preliminary interpretations of the APXS data, the formation of this native sulfur likely involved a novel and highly complex sequence of transport, deposition, and preservation that simply does not rely on standard liquid water evaporation. One leading hypothesis currently being investigated suggests that the native sulfur formed via the oxidation of hydrogen sulfide gas. Imagine deep underground, a fluid rich in sulfur dioxide and hydrogen sulfide trapped in icy structures called clathrates. Upon decompression, perhaps caused by the fracturing of rock or a sudden change in temperature, this fluid was exposed to the Martian surface. The hydrogen sulfide rapidly decomposed, precipitating pure elemental sulfur directly in place. But there is another fascinating twist to this story. Elemental sulfur is actually quite fragile. It is highly reactive over long geological timescales, especially if there is any water around. The fact that these fragile, crumbly sulfur stones are still sitting right there on the surface tells us something incredible about the climate. It implies an incredibly stable environment following their deposition. It tells us that after those catastrophic violent debris flows that formed the Gediz Vallis channel finally subsided, this region entered a profound, unyielding, and permanent state of aridity. The sulfur deposit was laid down, and then it persisted in a stable bone-dry environment for billions of years, perfectly preserved under the freezing Martian sky until a robotic wheel happened to crack it open. Whenever the word sulfur is mentioned in the context of planetary science, astrobiologists immediately pay very close attention. Sulfur is one of the 6 primary elements essential for life as we know it, alongside carbon, hydrogen, nitrogen, oxygen, and phosphorus. You will often hear scientists refer to this vital group of elements by the acronym CHNOPS. On Earth, organisms rely heavily on sulfur to build complex biological machinery. It is a fundamental building block of 2 absolutely essential amino acids, cysteine and methionine, which are strictly required to synthesize proteins. If you look at deep ocean hydrothermal vents on our own planet, where the light of the sun can never reach, entire thriving ecosystems are powered not by photosynthesis, but by chemosynthesis. In these dark depths, microbes utilize sulfur compounds to generate the energy they need to survive. Now, to be absolutely clear, no scientist is claiming that the bright yellow crystals in Gediz Vallis are direct evidence of Martian life. The chemical pathways required to precipitate native sulfur can absolutely occur through purely abiotic, meaning non-biological, geological processes. However, the discovery adds a vital, monumental puzzle piece to our understanding of Mars' past habitability. It definitively demonstrates that Gale Crater possessed an incredibly complex and diverse chemical environment. The fact that Mars was capable of hosting not just oxidized sulfates, but also reduced, elemental sulfur, means that a much broader range of chemical reactions was possible on the ancient surface than we ever previously thought. Think about it from the perspective of a hypothetical Martian microbe trying to survive in the waning, desperate days of the planet's habitable era. This diversity of chemical states, having both oxidized and reduced forms of sulfur in close proximity, could have provided vital, life-sustaining energy gradients to exploit. As NASA scientists meticulously noted, studying the Gediz Vallis region offers a completely new way to study how the presence of both water and the chemical ingredients required for life changed over time. Through the summer and early fall of 2024, Curiosity slowly maneuvered through this alien sulfur field, acting as an automated, six-wheeled detective at a 3-billion-year-old crime scene. The rover carefully examined the jagged sulfur stones, many of which were framed by distinctive white halos. Geologists suspect that dry avalanches originally brought these loose stones down the mountain. Later on, during brief, intermittent wet periods, where small amounts of water soaked into the surrounding terrain, capillary action and chemical weathering created these white, likely sulfate-rich crusts around the pure sulfur cores. These halos acted as a hard, protective shell that further ensured the sulfur's survival through the relentless eons. Looking out across the channel, Curiosity's mastcam captured breathtaking, high-definition 360-degree panoramas of the surrounding features. Among these features is Pinnacle Ridge, a towering, jagged debris mound left behind by the chaotic interplay of wet debris flows and dry rockfalls. Visual data captured here allows the science team back on Earth to reconstruct a rigorous, incredibly detailed timeline of events. They are mapping exactly when the river flowed, when the catastrophic mudslides crashed down the mountain, and when the final freezing winds swept the valley floor clean. On October 11, 2024, which marked the 4,331st Martian day or SOL of the mission, Curiosity used its mastcam to capture a final, poignant look at the field of bright white sulfur stones. The colors of the image were carefully adjusted by imaging specialists at the Jet Propulsion Laboratory to reflect exactly how the scene would look to the human eye under Earth-like lighting conditions. It stands today as a visual monument to one of the most serendipitous, unexpected discoveries in the entire history of space exploration. By November 2, 2024, Curiosity had officially headed west, capturing one last glorious panorama of the channel fading into the dusty distance behind it, leaving its own geometric wheel tracks permanently scarred into the Martian regolith. But having conquered the deep mysteries of the Gediz Vallis channel, Curiosity's mission is far from over. The rover is now embarking on a grueling, months-long trek toward an entirely new and equally perplexing geological target known as the Boxwork Formation. Spanning a massive area of roughly 6 to 12 miles across the slopes of Mount Sharp, the Boxwork looks from orbit like a vast geometric spiderweb draped over the barren landscape. On Earth, similar boxwork structures are occasionally found on cliff faces or deep within cave systems. They form when mineral-rich water precipitates solid minerals inside intersecting fractures in rock. Over vast stretches of time, the softer surrounding host rock erodes away, leaving only the hardened, intersecting mineral web behind, standing out in stark relief. However, the Martian boxwork is utterly unique, both in its staggering scale and its formational timeline. Just like the Gediz Vallis channel, these subterranean structures materialized late in Mars history, right as the surface water was permanently retreating and the planet was plunging into its deep freeze. Planetary geologists have highlighted the immense astrobiological potential of this upcoming target. These ridges will include minerals that crystallized underground, where it would have been significantly warmer, with salty liquid water actively flowing through the subsurface fractures. Because the surface of Mars was rapidly becoming increasingly inhospitable, hostile, violently irradiated, and frozen, any potential microbial life that might have existed would likely have retreated deep beneath the crust, following the receding water table. Early Earth microbes could have survived in a very similar environment. That makes the boxwork an incredibly exciting, high-stakes place to explore. As Curiosity wheels its way toward this subterranean graveyard of crystallized minerals, it carries with it the profound lessons learned from Gediz Vallis. The grand transition from a blue, water-rich world to a red, desolate desert was not a gentle fading of the light. It was a violent, complex, and chemically rich epoch. It was marked by catastrophic debris flows, wild shifting climates, and the highly localized precipitation of life-sustaining elements like native sulfur. The exploration of the Gediz Vallis channel stands as an absolute masterclass in the value of sustained, on-the-ground planetary exploration. When NASA engineers first designed the Mars Science Laboratory over a decade ago, they could only dream of the intricate geological nuances it would eventually uncover. Orbiters circling high above the Martian atmosphere can identify broad mineralogical trends. They can map out the large expanses of clays and sulfates, but they absolutely cannot crack open a rock. They cannot witness the bright, blinding flash of yellow brimstone hiding just millimeters beneath a dusty facade. The discovery of pure sulfur in the Gediz Vallis channel proves beyond a doubt that our understanding of the red planet is still very much in its infancy. Mars is not merely a dead, static rock floating in the void. It is a complex world with a rich, dynamic, and unexpectedly beautiful history. It possessed an environment where rivers raged long after they were thought to have completely dried up. It was a place where entire mountainsides gave way in thunderous avalanches, and where pure elemental sulfur crystallized in hidden oases against all scientific odds. As curiosity continues its solitary, relentless climb up the lonely slopes of Mount Sharp, leaving the yellow crystals and boulder-strewn canyons far behind, it serves as humanity's tireless, mechanical pioneer. With every single turn of its scarred, battered aluminum wheels, it redefines the very boundaries of planetary science, ensuring that the true story of Mars' climate history is written not in broad, speculative strokes, but in the precise, shimmering light of a cracked Martian stone. Thank you for tuning in to Fun Facts Online. We hope you enjoyed this deep dive into one of the most remarkable discoveries on our neighboring planet. Keep looking up, keep wondering, and we will see you in the next episode.